Okay, let's get started. Not many people here today, so if you're here, feel free to ask questions. Otherwise, we'll just get started. And then today, at the end of class, I'll be going over Project 2. So if you have questions about Project 2, there'll be an opportunity for you to ask questions about Project 2. All right? First of all, any questions about course logistics or material before we start? Nope. All right. Okay, so today we're going to continue discussing K-space trajectories and pulse sequences, and we'll get into sampling, aliasing, and resolution. So hopefully by the end of the class, you'll sort of understand what happens behind the scenes when the technician sits down to the MRI machine and enters in the parameters for scanning. Before we do that, there were some questions about the MRI lecture pre-quizzes. And so the idea is, I think there were two questions where uh, the percentages of correct weren't as high as they typically are. So let's go over that. So just to remind you, if I have a K-space trajectory, uh, a point in K-space like this, then if I have K-space, if I have a point here, then the pattern will be like this. Or if I have a point here, then the pattern is also like that, right? So if I have a point here, the pattern will be like this. And if I have a point here, the pattern will be like that. All right. So based on just that, there's really only one correct answer in the pre-lecture quiz. Okay. And so I think maybe, I forget what the thing was, but I think uh, the signs were just flipped on what a lot of people picked. All right. Any questions on that? Okay, and the other thing that sort of reminder is spins precess with the left hand rotation or clockwise rotation. Okay, so if you think about spins precessing in the XY magnetization plane, we're always talking about spins precessing this way. Okay, so we're going clockwise rotation, a precession, and therefore the angles are becoming more negative. Okay. And so that was sort of, I think there was just a sort of a sign issue with some of the answers. All right. Okay. So any questions? All right. So this is theta less than 0. Okay. So let's go ahead and review a little bit about where we are. So in previous lectures, we found out that where we are in K-space determines on, this is the time integral of the gradients. So you can think of it the area under the gradient. And so we just take the area and you multiply by gamma over 2 pi. Um, and so you do that individually for both kx and ky. And so the gradients control where we are in k-space. And so really the design problem that you're going to have on the homework is design trajectories that take you through k-space in a certain way. All right. So let's just do this simple example so for the homeworks, you're going to need two things. One is you're going to have to be able to just relate areas under gradients to where you are in K-space to be able to do the homework. The second thing you're going to be able to do is to figure out the sampling stuff that we'll talk about later in this lecture. And so the first two MATLAB homework problems are really about just computing areas and making sure you meet certain sampling criteria. So if you can do those two things, then you should be fine with the homework. All right. So let's look at this first pulse sequence. So this is the pulse sequence where I'm showing you GX and GY. And GX goes up to 10 gauss per centimeter for the first 2 milliseconds, and then becomes negative 10 gauss per centimeter for the next 2 milliseconds. Whereas GY ramps up to 10 gauss per centimeter and then ramps down. And so the first question you're asked is, question A is, what are KX and KY at 4 milliseconds? So at this point in time, what is the area under those gradients? Okay, so this is meant to be a fairly simple question. So what's the area at 4 milliseconds, what's the area under that gradient? 0, yeah. Okay. And what's the area under the GY gradient? Yeah. So if you just get that, that's going to help out a lot with the homework because that's sort of a nice sanity check. All right. So then next thing is what's the area at 2 milliseconds, right? And so here you're given gamma over 2 pi at 4258 hertz per Gauss. And so let's look at that. We could say, well, it's just, oops, 4258 hertz per Gauss times 10 Gauss per centimeter, right? Times the time, which is 2 times 10 to the minus 3 seconds, right? So I have something on the order of 4,000 times 80 times 10 to the minus 3, right? And that's approximately equal to 4 times 80, is that right? All right, so what did I screw up here? Anyone see the error? Well, this should be 20, right? 20 times 2 times 10, it should be 20, right? Okay, so that's 80. Okay, so the answer, if you look at those answers, then it should probably be about 85 inverse centimeters. Okay, so that's where you are in kx. And what about ky without doing any math? Where are you in ky? So what's the area under this guy compared to the area under the first guy? The half of it, right? So then the answer is clearly this guy. All right. So if you can do stuff like that, you'll be fine on the homework. It's basically the areas under rectangles. All right. So everyone here can figure out the area under a rectangle. So just as you're doing the homework, just realizing all you're doing is computing areas under rectangles, right? Okay. So last time we talked about the spin warp pulse sequence, and the idea is we have, this is called the readout gradient, also called the frequency gradient, and this one is called the phase encode gradient. Okay. And the idea is we're trying to use repetitions of this basic motif to go through k-space. All right. And so we're going to go through, we found out that up to this point, let's say this is time t1, it goes here. So this is at t equals t1, we get out to this point in k-space. Okay. And then after that time, we only have the gx gradient on, and so that just zooms us across k-space like that. Right? And so we've required one line through k-space. The next time we go about, and then we just repeat this process where the thing that you notice is this is the thing that's changing. Okay, the amplitude of the phase encode gradient is changing. The gx gradient stays the same. It's doing the same thing every time. It's always going out and back, out and back, out and back. So the only thing that's changing is the gy gradient, which is determining how far along the ky axis you're going, right? And so we can see that here. So the first gradient takes me out to this point. The next gradient starts off at a different point and then just zooms across k-space. And this gradient just goes there. And then if we add some more gradients, they took us into positive ky's like that. All right. So that's the basic spin warp pulse sequence, which is the bread and butter of all MRI pulse sequences. Okay, so now we need to answer the question of, okay, how should we go through k-space? And this gets us to the question of k-space sampling. So the things we're going to introduce are some terminology. We're going to introduce field of view, which you probably saw already in the CT part. So FOV just stands for field of view. Okay, and so we have a field of view in the X and the Y direction. That's basically when you're doing a scan, you just basically, the technician has to tell the scanner how big approximately is your object. All right. And then the other thing you're going to tell the scanner is what resolution do you want? Do you want 1 millimeter voxels or 2 millimeter voxels? Or you could even have 1 millimeter this way, 2 millimeters this way. So that's up to you to decide. All right. So from those four parameters, we're going to now derive four parameters in k-space. Because remember, we're acquiring the data in k-space. And so therefore, we need to understand what's the sampling, the delta, what's the increment of sampling you do, which is delta kx or delta ky, and also how far out do you go in k-space, which is wkx, wky. All right. So that's the thing we're going to try to figure out. So you saw some of this already in one of your homework assignments, the effect of what happens if you don't sample finely enough in K-space. Okay. So this was the image and this was its K-space or its Fourier transform. And here I've downsampled. Okay. So basically I've gotten rid of every other vertical line in K-space, right? I just like zeroed it out, which is what you did in your homework. And then you did inverse Fourier transform. And what you saw was this aliasing. Okay. You should have seen in your homework that the pattern repeats itself. Okay. So this is obviously something you don't want to have happen in a clinical setting, right? If you're going to go and get your brain scanned for surgery, you want to make sure that your nose is not protruding into your visual cortex because it's going to make it harder for the physician to figure out, what to do with your procedure. Okay, you in the homework, I believe you also did here on the top, we've taken out every other line this way. Okay, and now you see the pattern is repeating this way. Okay, so that's a form of vertical aliasing. And then in this bottom one, we've gotten rid of every line this way and every line this way. So now we're repeating both this way and also this way. All right, so that's what we want to understand. And obviously, when you're designing your MRI sequence, one of the criteria is you should not have aliasing. All right. So let's take a little example of sort of why there's aliasing. Remember, we're always looking at what the spins are doing, okay? So this is like 6 different spins at different points in space. And we're assuming that they're in the presence of gradients. So these go slower and these go faster. And so what happens is, and we're assuming we're in the rotating frame. So we're going to see the accumulation of phase. And so what we did before is we said, okay, well, if we do one time step, maybe this is at isocenter here, right? So that spin is not changing its phase, but everything to the right of that spin is acquiring more phase, and everything to the left is getting negative or positive phase on this, going counterclockwise this way, clockwise on this side. All right. Um, and So these are all going clockwise. These are all going counterclockwise. All right. And then the more we allow the spins to progress, they just keep going in that accumulating phase. So remember, in MRI, we don't actually get to see what any individual spin is doing, right? If we could already see what the spins are doing, we wouldn't need to have the MRI system, right? So the whole idea is you want to look inside an object that you can't look into otherwise, right? The only other way you have of looking inside someone's brain is to like freeze them and slice them up, right? So that's not a really good option. Or in the future, there'll probably be like nanotubes you can put into their brain and maybe navigate through their brain. But currently, probably no one wants to have that done, right? So your best option right now is to have a CT or an MRI, possibly ultrasound, okay? So basically, all these are ways of we want to see what's inside an object, but we really can't get in. We don't want to damage the object. So all we get to see is the summation of what all the spins are doing, right? So basically, if 2 spins in different positions are doing exactly the same thing, when they come into the summation, they have the same phase at every time. And so those 2 spins will appear to be coming from the same place. All right. And so that's what aliasing means. So if you look at this thing here, these 2 spins over time are always doing the same phase over time, okay, over the time steps. And so when they come into the summation or the integral, we really can't tell them apart. And so we have to assign them to the same place in space. And so those 2 points we would say are aliased, right? Similarly with these 2 spins, they would also sort of look like they're doing the same thing. And so they would also be aliased. So what can we do? Like, how could you make these 2 spins, like these 2 spins with this sort of sampling, they look the same. So what could we do to make these spins look different, right? Because look at this one, this spin went 180 degrees. Let's see, what did he do? He went all the way this way, right? And this spin went all the way. Oh, wait, did he? Let's see. What did they do? No, this spin just went this way, right? Yeah, sorry. Let's get the I get the, okay, well, I can't get my eraser right now. So this spin went that way. So one spin went clockwise, 90 degrees. The other spin went minus, you know, whatever that is, 3 pi over 2 the other way, right? So they end up at the same place. So what could we do to make those spins look different? Well, here's the answer here. I guess I already went to the answer. We want to add additional time points, right? We don't want to take a big step from here to here. We want to look at what the spins did in between, okay? Because in between, this spin went 45 degrees and this spin went minus 135 degrees, okay? So if we just made our sampling a little finer, we could sort of tell, oh, those spins are actually different, right? And so similarly here, now this spin and this spin, they look different at those time points, all right? So we introduced additional samples to help us tell, oh, these two spins are actually acting differently over time. So then when they come into the integral, we can sort of tell they came from different parts of space, all right? So that's how we deal with aliasing. I'm going to skip this for now. So let's look at the process of sampling. So you covered a little bit, you guys did a little bit of this, right, with CT, right? Okay, so let's go through this pretty quickly. So remember, if I have some continuous function g of x, if I want to sample it, I'm just going to get discrete functions g bracket n is equal to g at n delta x, where these are, well, this is just integers, integer values, n, and this is the delta x here. So this is x here. Okay. So remember, the function we do to use that is the comb function, which is just looks like that. It's just also called impulse train or bed of nails. It's just basically direct delta functions at the integer values, right? And then we can also, we want to scale the comb function. So if we want to scale it, we just take comb of x over delta x, and that gives us a spacing of delta x, right? So remember, the Fourier transform of a comb is just a comb, so that's good to know. So if we scale a comb function, we get this here. It's a comb of kx delta x. And this just has in the x domain, in the k domain, now the spacing is 1 over delta x. Okay? So what if the spacing in one domain is delta x, the spacing in the other domain will be 1 over delta x. All right, so that's shown here, where I've got delta x and 1 over delta x. And so let's take a look at this. So basically, this would be sort of my object here, right? And this is its Fourier transform. And then we're going to sample that Fourier transform, right? So what MR does is we're not going to get every single point in Fourier space. So we're going to sample the Fourier transform, all right? And so that's shown here. And the question is, if I sample the Fourier transform of this object, so I have the sinc function, right? Obviously, if I take the sinc function and do the inverse transform of it, I get the rect function back. But now the question is, I sample that sinc function, I have those samples. If I do the inverse Fourier transform of that, what's my object going to look like? Right? And how should I sample my Fourier transform such that when I do the inverse transform, I get back something that looks like my object? Right? So that's the question we're going to answer. So remember, Fourier sampling, we're going to use a comb function where we're just going to sample with delta kx increments. All right. So the math is all there, but all you need to know really is that the increments, we're going to call them delta kx. All right. So what does that mean? It means that I'm going to take this is my Fourier transform here, right? That's my sinc function. That's Fourier transform of my object. I'm going to multiply it by a comb function to get my sampled function, okay? So I've multiplied in one domain, so that means in the other domain I have to convolve, right? So that just means I take my object, my nice rect function, and I'm going to convolve it with something that's spaced now 1 over delta kx, right? So now this just gives me my replicas, right? Because remember, every time you convolve something with a delta function, it just moves that object to there. So I have all these delta functions. So it basically says, okay, here's a delta function, put an object here. Here's another delta function, put an object here. So I'm just going to take my object and I'm going to repeat it. Okay. And so you can sort of see where we're going is eventually, if those repeats overlap, then I'm going to have aliasing. If those repeats don't overlap, then I'll be okay. So we just want to set up our MRI sequence so that we don't get overlaps. All right. So that's basically the Nyquist condition. So the user gives you a field of view, and that tells you, I think my object's going to be this big. So your only job is not to make those objects overlap. Okay? So it's pretty simple, but it's the fundamental thing. So the idea is this spacing between the objects is 1 over delta kx. So you just need to make sure that 1 over delta kx is bigger than your object, right? If that spacing is smaller than your object, then you're going to have overlap, right? And so that's all you're trying to avoid. So that's the Nyquist condition. So obviously, if you don't satisfy it, then that's when you get aliasing. Here's a simple example where we don't satisfy Nyquist, where here's my sinc function on the left, and I've taken these, I'm sampling it like this, right? I'm taking samples every delta kx equals 1. And so therefore, everything is 0 except for the middle, right? And so that's basically an impulse function, right? So if I take that and I take the inverse transform of it, the inverse of a Dirac is just 1 everywhere. And so in this case, those rectangles overlap, like they're just sort of, I have a rectangle here, I have a rectangle here. So they don't really overlap, but they're just sort of right next to each other such that when I look at my image, it's constant everywhere. Okay. So we talked about 1D comb functions. Obviously, in imaging, we need to have 2D comb functions or 3D comb functions. So it's the same thing. You can take a comb of xy, it's just comb of x times comb of y. So everything we've derived before applies. So you have comb of x over delta x, comb of y delta y. This allows you to have different spacings, right? Because you might have an object that is wider than it is tall or taller than it is wide. And so your requirements may differ in the x and y directions, right? Okay, so we just have in 2D K-space sampling, we're just going to have uh, something with spacing of delta kx and spacing of delta ky. And so this is basically the bottom line. So here's my object here. And here I'm taking the Fourier transform here, right? And now I'm sampling here, right? So that this spacing here is delta kx, and this spacing here is delta ky, right? And I multiply my original Fourier transform by that sampling pattern. So here I have my samples. All right. And then that means I've multiplied in one domain, so therefore I must convolve in the other domain. All right. And so remember convolution. So now I've the inverse Fourier transform of this guy is just have spacing 1 over delta k. Okay. So it would be like 1 over delta kx in this direction and 1 over delta ky in this direction. Right. So these are just like impulse functions spaced in 2D K space. And so I just take my object and I just plop it wherever I have direct delta function, I just plop my object. Right. And so I end up with these replicas. Right. So that's basically all you need to know about how to sort of the sampling of K space. So the Nyquist conditions are simply 1 over delta kx is greater than f of v of y, and 1 over delta kx is greater than f of v of x. And for your homeworks and your projects, even though this is an inequality, the convention is you just set it equal. All right. So if I give you an FOV of x, right, then you're just going to say, oh, delta kx equals 1 over FOV of x. Okay. So you just apply the equality for your constraint. So that's what you'll be doing. Right. Similarly, if I give you FOV of y, then delta ky equals 1 over FOV of y. Okay. So let's give you a problem to think about for a little bit. Here's my object, because if you can understand these problems, then when you get to your homeworks, then it should be fairly straightforward. All right. So here's my object, g of x, y. It's a cosine, a two-dimensional cosine multiplied by two rect functions, one in x and one in y. So I'm going to give you a minute or two. Feel free to discuss this with your neighbors. What should my delta kx and delta ky be for this object? Right now, I'll open up a poll online. The people online can respond. Let's see. Okay, let's check in. So first of all, what's the field of view of this object in the x direction? How big is this object in the x direction? Anybody? 3. Okay, so it's 3 whatever units it is, all right? And what's the field of view in the y direction? Anybody else? 4, right? Okay. So everyone okay with that? Okay. So therefore, we just apply the things. Obviously, the answer is C, which is I think what most people got. All right. So that's um, essentially it's a fairly easy computation. You just need to know what the field of view is, right? And so essentially in every MRI system, when you look at some of the software, there's typically going to be a couple of lines saying, okay, the user entered field of view, we're going to convert this into delta K, all right? Because then once I know the delta K, then I can go figure out what the gradients are. Okay, the other thing we need to know is windowing. So the windowing is essentially, it's like I'm not going to go out to the far reaches of K space, right? Because the more farther I go out, the more time it's going to take to collect data. And plus, the farther I go out, it's just going to be mostly noise, right? So I really only want to collect K-space data where I think I need to collect K-space data, all right? So that process is known as windowing. So instead of going out to minus infinity, infinity, I'm just going to collect K-space data within some window of K-space, all right? And so that's noted here. This is the Fourier transform, the ideal Fourier transform that I would get. And I multiply by a window, which basically says what I actually acquire is just data within some window. Okay. And so here, this is a multiplication, right? And therefore, I'm going to take my original object and convolve it with the inverse transform of my window. All right. So you already saw window, and I think several of the project one projects looked at, windowing in CT. So this is a different, you're seeing windowing in certain a different setting right now. Okay, so let's see what that looks like. So here's my object. Okay, here's its Fourier transform. And it's a sinc function, right? And let's say I just said, okay, I want to collect the sinc function out to the edges. But then I realized, well, actually, maybe I don't have the and here I don't know why I called it M, but this is the window. I want to just collect the data in some window, right? So I multiply that two-dimensional sinc function by a rect function, and so now this is the windowed Fourier transform. So you see it's 0 everywhere outside the rect, and I'm only collecting data within some little window. Got it? Okay. So I've multiplied here, right? This is a multiply. So now I need to convolve here. Okay. So my window was a rect function. So that means its inverse Fourier transform is a two-dimensional sinc function, right? So basically I'm taking my object now and I take my rect function, I have to convolve it with this two-dimensional sinc function, which sort of is like, falls off like that. And so therefore, looking from the top, the two-dimensional sinc function sort of looks like this object like that. So I essentially, similar to what you did on your homeworks, is essentially going to blur out my object, right? So in your homeworks, you had a two-dimensional Gaussian function, which you convolve with your square or your cross or something like that, right? Here, you're taking a two-dimensional sinc function and convolving that, and you're going to get similar effects because that sinc function has some width to it, right? So this is a blurred object. Okay, so it's like a 2D sinc. So basically, so this means that the size of your window in your Fourier space, that's going to have an effect on your resolution, right? Because if you think about it, low resolution means the object is more blurry, and the higher the resolution is, the less blurry the object is, right? Okay, so that's just showing this here. Basically, we have these rect functions, and we use delta kx and delta ky to represent how large those windows are. So if I'm in K space, I basically just have the width WKX and the height WKY. Okay? And so therefore, in the image space, I'm going to be convolving with sinc functions that look like this. Okay, so this is going to be a sinc function where its first zero is 1 over WKX. And this will be a sinc function where its first zero is 1 over WKY. All right. So for imaging, at least for basic imaging that we're doing, rect functions and sinc functions are super useful. All right, for getting intuition about what's going on. Okay, and so what we want to know is what's the effective width of a sinc function. And so essentially, this is showing you the sinc function here, right? And the effective width is just, what's the width of a rect function that has the same height and the same area, and that would be the effective width. And it turns out the effective width is pretty easy to remember. It's just the location of the first zero. Okay, so basically, if I have sinc of, say, 3x, 3kx, right? This has effective width. The width in the image domain would be 1 over 3. Yep, question. Yeah, that's a great question. So remember, we're going to be convolving with these sinc functions, right? We're going to take our object and we're going to convolve them with sinc functions. So we want to know, am I convolving with something that's skinny or fat? So I want to know what's the effective width of my sinc function, right? If the effective width of my sinc function is really large, that means I'm going to have a lot of blurring, right? If the effective width is very small, then I'm going to have less blurring. Okay. So this is just the effective width. So this is effective width of, say, a sinc function.
So is that like the effective blurring that we will see in our real object after?
Yeah, I'll give some examples of that. Yeah. Okay. So it sort of makes sense. Basically, look at this. This is the effective width, and you're saying it's 1 over WKX, right? So that makes sense for a sense. If I make WKX really big, I go way out into K space, I collect as much data as I can, then that effective width goes down, right? Because I'm sort of, if I can go out to infinity, I basically can recreate my object, right? So therefore, the effective width will go to 0. There's no blurring introduced by my windowing. As I collect less and less K space, as you saw in some of your homeworks and examples, let's say I only collect a little bit of K space, then I wouldn't expect to have a very good image reconstruction. And therefore, and it actually leads to a lot of blur. I'll get a very blurred image. All right. Um, so yeah, so let's skip that for now. Let's go on to this windowing example here. So let's assume that I have this as my object. So my object is going to be a delta function at 0 and a delta function at 1. Okay, so this is the classic example. I have 2-point objects. If my imaging system is good, then I should be able to distinguish these 2-point objects, right? And so in my imaging system, as my imaging system gets better, those two objects should become more easy to discriminate. So let's look at an example of this. So um, remember, I'm convolving each of those with a sinc function. So in this case here, WKX equals 1. So that means my effective width is equal to 1. Okay. And let's see what happens there. So here I have the sinc function. The blue sinc function here is sinc function from one dot, and the green is from another dot. Okay. So in this case, those two sinc functions, if I sum them up, the green and the blue add up to the red. So in this case, I'm at the limit where those two dots become one dot. Okay, so I really couldn't resolve those two dots, right? So that's another way of looking at resolution. Can you resolve whether there's two dots or not? Now look at here. Now I make WKX equals 1.5. So now my effective width has gone to 2/3. So those two sinc functions get narrower, right? So now when I convolve each with a sinc function, I've got two sinc functions, but they're narrower. So now when I sum the two up, here in red, you sort of see, oh, I'm sort of seeing something with two peaks. It's not huge, but it's enough that if I had enough SNR, I would be able to tell, oh, there's actually two dots there. Okay, so that's showing you how the more out, if you far out you go in K-space, your ability to resolve two dots improves. Right? Here I made WKX equals 2, so the effective width is now 1/2. Now you see the sinc functions are getting much narrower, right? And now if you look at it, that red curve overlaps with the green and blue curves where they are. And so now I have really good resolution of those two dots. All right. So that's sort of what you want to have in mind. If the higher the resolution, if your user tells you, hey, I want a really high resolution image, you're just like, great, you just have to go farther out in K-space. Okay. It's going to cost you more time and money, but if you want that, we can do it. All right. Okay. So let's put everything together. So here's my object. Here's its Fourier transform. Okay. First thing I'm going to do, and we're going to do everything in the Fourier domain first, because that's where we're doing things. First thing I do is sample, right? So this gives me my samples, right? And then I window, right? And so what you're seeing here, it's a little hard to maybe see on the, you can sort of see it, but you basically have a bunch of samples within a window, okay? So that's the data. This is the data we acquire. So remember, these are all multiplications, right? So they're going to transform into convolution. All right. So this means take your object, replicate it. Okay. So it's going to be replicas. And in addition, every replica, you need to smooth it out or filter it with that sinc function. So what you're going to get here are blurred replicas. Okay. And as long as you satisfy the nice condition, those replicas don't overlap. So you don't have aliasing. And then if you set your setting correctly for your resolution, then the blurriness will be acceptable. Okay. So that's just shown here where basically the convolution with the sort of this gets you the replicas and convolution with the sinc does your blurring. Okay. So that's when for your homework assignments, basically, you just need to make sure you use these, apply the design rules correctly. So what are the design rules? So this is to avoid aliasing, right? And remember, we could just set delta kx equal to 1 over FOBX. Okay. And then here, the resolution should be that WKX is greater than 1 over delta X. Okay? You always want to go out enough such that you satisfy your resolution. And then for the design issues, you can always just set those to equal to equality. Okay, so typically you're just going to be told the user wants a certain resolution, and then in your code, you just sort of set those windows to that size. All right, so it's fairly straightforward to apply that. Okay, so let's take it for a few minutes and look at this one. So uh, once again, it's the same object here. And now you're asked, what are kx max and ky max to satisfy this? And just so you know, we're going to assume that, like, if this is WKX, KX max is half of that. Okay. So basically, if my window is symmetric around 0, then it means that the biggest positive and biggest negative, we're just going to assume is half that window size. Right. So let's go ahead and take a few minutes to look at that, and then we'll regroup in a minute. Okay. So you're asked to sort of, the first thing you want to think about is what would be a reasonable choice for the resolution of this object? Okay, so this is a certain object, it's going to have a certain resolution to it. And then once you know that resolution, so you want to sort of think about, what are my delta kx and delta y here? Okay. Like I've got this two-dimensional cosine, so what sort of frequencies does it have in it? And therefore, what would be the reasonable kx and ky max parameters to use for this object? Okay, how far out do I actually need to go into K space to sample this object correctly? All right. So timer. Okay, so let's look at this object here. So it's got the form cosine. So we sort of already dealt with the rect function before, right? Because that dealt with field of view. So let's just look at the cosine. So I've got 2 pi. It's got the form kxx plus ky, right? So we know kx is equal to 3 and ky equals 2, right? So the frequency this object has is goes out to kx of 3 and kx of 2. So based on that, which answer would make the most sense? Sorry, can I say that? D? E? Okay. Okay, so that's one possibility. So we might say, yeah, we have to sample twice that, right? Okay. So for example, this is something that has kx of 3 and ky of 2, right? So one thing is we might think, oh, like from Nyquist theorem, we know we have to sample twice the highest frequency. Okay. Any other thoughts on this? Okay. So that's a good way of thinking about it, but it turns out we don't actually have to do that in this case, right? It turns out that we can just go with B. Okay. because basically we just have to make sure there is an object at that frequency. And so in K-space, we just need to make sure we sample at that object at that frequency. Another way of thinking about this is if you look at something with a kx equal to 3, that means that this is something that cosine that varies with something like a period of 1 over 3. Okay, so that's the period of variation of that cosine. And so you think about it this way, here it's positive and here it's negative. Okay, so if I made the simplest object with that frequency, I could imagine an object that's like this and like that. So that's the period of variation, right? So a reasonable sort of assumption for what my resolution would be 1/6 for my delta x, right? Okay. And therefore I would say WKX should equal 6, okay, which is that 6 that you got there. But remember, KX max equals WKX over 2, which is equal to 3. Okay, so that's another way you could get at why that sort of makes sense. So the idea is in Fourier space, if you need to get that frequency, but you've sampled that frequency, then that's sufficient because you're sampling, remember, you're not sampling in image space, you're sampling in Fourier space. All right, so that's one thing to think about. Okay, so where does this come into play? So we're going to show you, this is sort of what an MR, it still looks like this actually. It's quite old, but this is what the user interface looks like if you were to sit down at like a GE MRI system, all right? So let's take a look at what is entered. So here you see there is a field of view, okay? In this case, 24 would mean 24 centimeters. Okay, sort of just understood based on human-sized things. It's, centimeters is sort of the understood thing. Slice thickness we'll get to later. And then here, notice here, we don't actually specify resolution, but we do specify frequency and phase. Okay? And what this means is that this is going to lead to delta x is equal to 24 over 256. So it's basically saying I want, over my field of view, I want 256 voxels in that field of view. So that's going to be my x resolution. And then my y resolution, the delta y equals 24 over 128. So that's how they specify resolution on a GE system. Sorry? Oh, okay. So remember GX for spin warp, the GX gradient is always is like the readout or frequency. And GY is typically the phase encode. And that was the gradient that we sort of incremented like each line. So that's sort of like it changes the initial phase along KY. Yeah, okay. Okay, this is what this similar to what the user interface looks like on a Siemens system. All right, so let's see how they specify it here. I forget exactly how they do it. So here they actually specify, you can sort of see here, FOV in the read and FOV in the phase. So this would be my field of view of X is equal to 2, and here it's in millimeters, okay? So now they've actually told you what the units are. The field of view of phase is 100%. So they don't actually let you enter in the field of view in the y direction. They're just saying what percentage of the readout direction field of view is the phase. And so in this case, the field of view of x, field of view of y would also equal 220. All right. And here, yeah, and then on this one, actually, you have to go to a different page to get to the resolution. So actually, on this page alone, you can't really see what the resolution is. So you'd have to go to a different page and enter in the resolution. All right. Okay, so this is this picture we looked at before. And so now we're going to put everything together and we're going to apply it to spin warp pulse sequence. So we'll spend the rest of the class going through how we would apply these design equations to spin warp pulse sequence. And so the caveat I'm going to give you now is this is one way of applying the design parameters. So you get to see an actual application of how we apply the design parameters. If you just repeat what I'm doing for your homework assignments, you're not going to get the right answer. Okay. So the idea is we're going to apply the principles, and then your job is to apply those principles to two different trajectories. There's going to be a square spiral trajectory and an EPI trajectory. Like that one will go through K-space as a spiral, the other one will zigzag through K-space. Okay. So the concepts of where you are in K-space is based on the areas and the KX and KY, the delta KX, delta KY, depending on the field of view. All those things still apply, but the way the where are you in K-space related to the gradients is going to be different. So just make sure you understand the principles and don't just if you just copy and paste these equations to do your homework, it just won't work out. All right. So that's the caveat. So just to remind you again, the spin more pulse sequence is we're going to go line by line by line by line through K-space. So for every line, we just have to figure out, how do we set up these gradients? Oops. We're trying to design these gradients such that it will accomplish what I want. Okay. Um, so this is another example. So remember, every time I'm applying a GY gradient, it's just taking me out to some initial point in K-space. Okay. And then it just holds that where I am in KY. Okay. So I go out to some KY and that I turn off the gradient. And so I hold that. And then the KX is always doing the same thing. It's just zooming out one way and then coming back, zooming out, coming back. All right. Okay. So let's first of all look at how sampling in KX gets done. All right. So this is going to give me my delta KX. So that's really pretty much done in some way. I mean, all this is done with the electronics, but they're done in different ways. So I'll just give you a very high level overview of how it's done. The idea is, remember, our MR signal comes in. We do our demodulation, which we talked about in a previous slide or lecture. And then we're going to typically do the sampling here. Okay. So ADC stands for analog to digital converter. And everyone has one right now, right? Everyone has at least one of these on them right now, if not more. Okay. So I actually have at least three right now on. So, right, I have one in my iPad, I have one in my phone, and I have one in my computer. At least one. There's probably several of them. Okay. So anything that's taking pictures, anything that's recording audio, everyone, this would not have been the case 30 years ago, right? People weren't walking around with analog to digital converters 30 years ago. Now everyone has them. Okay. And so these are doing two things. One, first of all, they're sampling. Okay. So they're taking samples in time. And they're also doing something called quantizing, right? So when you how many bits of representation. Okay. So we're not really going to focus on quantizing so much here, but we're going to focus on the sampling, right? So essentially, these are going to sample every delta t, right? So the MR signal is coming in. Now you have to sample it every delta t. Okay. So we're going to sample in time. And so the sampling is done in time. So now we just need to, how do we relate delta t to delta kx? Okay. And so it's going to be through the gradients, right? Because as we're zooming across K-space, how fast we zoom across K-space depends on how big the gradient is, right? So let's take a look at how that looks. So remember, this is the gradient. This is the part of the gradient where we're zooming across K-space, right? That's that part where everything is flat, right? And we're assuming as we're zooming across, we're going to take a sample every delta t. Okay. So now the question is, how much do I move across K-space within one delta t? And for the simplified example, it's pretty simple. It's just the area under the gradient, right? So that means delta kx is just gamma over 2 pi times the area of my gradient, gxr, times delta t. All right. So that means typically I'm going to know what delta kx is, right? Because I can solve for I know the field of view, so I can solve for delta kx. And then typically what happens is, at least for this class, you'll typically be given one of these. Like you'll say, okay, the maximum gradient you can have is this, so you can figure out what your delta t is, or you're told you're sampling at delta t, so then you just figure out what the gradient is, right? So fairly simple. Here's an example. The user says, I want a field of view of 25 centimeters, which is a pretty good, that's a pretty standard size for a human head. Okay. So if you meet anyone with a head larger than this, that's pretty unusual, but could happen. Okay. And then you're also told that delta x, delta y, the resolution is 0.1 centimeters. Okay. So typically when you're given these things, a good sanity check is to figure out, well, how large is my image? Okay. So for this one, how many samples, how many voxels would I have in the x direction if this is the image that they're asking for? Yeah, I'd have 256 voxels because 5.6 divided by zero point 0.1 is just 256. Same thing here, 256. So that's a good thing to keep in mind. I'm going to have a 256 by 256 image at the end of the day. That's what the user is asking for. All right. So now I say, okay, well, my field of view is 25.6, right? And I can plug in, this is what I know what my delta kx is, right? And in this case here, I'm told that delta t is 32 microseconds. So you can just then solve for GXR, right? You know the FOV, you know gamma over 2 pi, you know delta t, and so therefore you can just solve for the missing parameter, right? So in all your sort of, when you're doing your MATLABs, there's just always going to be some things you solve for, all right? And those are typically going to depend on meeting these area constraints, right? So in this case, I would solve for GXR and I would get that equals 0.28675 Gauss per centimeter. All right. So that's one. So I've solved one of the gradients. Yes. Um, for this one, I just picked something that's sort of a common delta t. We'll get into that later. The delta t turns out to be um, determined by a couple of things. One is how fast the hardware can go. Okay. So given sort of typical hardware, 32 microseconds is a reasonable thing. Also, more delta t is, the more averaging I'll be doing, right? So basically, if I want to reduce noise, I can also increase delta t. We'll try to touch upon that sort of at the end of the course. Okay. But for all your homeworks and stuff, you'll just be told what delta t is or solve for it. Okay. Okay, now let's look at the resolution. Remember, we were told the resolution was we want delta x equals 0.1 centimeters. Okay. So remember, delta x, if I know delta x, delta x is 1 over wkx. So wkx is how far out do I need to go in k-space? Okay, so how far do I go in k-space? Well, from this side of k-space to this side of k-space, that's accomplished by this gradient area, right? That gradient takes me from one side of k-space to the other side of k-space. So the delta kx is just simply the area under that entire gradient. Okay, so the wkx would just be my gamma over 2 pi times my gradient, which I just solved for, right? I know the side of the gradient times tau sub x. Okay. But I know that this is made up of little samples delta t, right? So in this case, we know tau sub x should equal the number of time points I need, let's call that nx, times delta t, right? Okay, so I'd be essentially solving for how many samples. Let's actually call that nkx delta t. So basically, how many samples do I need to acquire? That's going to tell me how long I have to play that gradient out, right? So if we do that, we can actually solve for delta tau of x, and we're going to get it equals 8 milliseconds. Okay. And that's also equal to n read times delta t. Okay. And it turns out that if I solve for that, then I just get 256, which makes sense because I want an image that has 256 pixels along the x dimension. So sort of by conserving information, it means that I need to have 256 samples along kx, right? So that's how you would solve for the readout gradient. You basically You're given your delta x. You know your gamma over 2 pi. We solved for GXR before, so you're just solving for this tau sub x. All right. And the sanity check is just that tau sub x is equal to n read times delta t, and this n read sort of makes sense. All right. Once again, it's just solving the design constraints and computing areas. Okay. Okay, so let's look at this one. You're asked to design a spin warp readout gradient to achieve a field of view of 2 centimeters and a resolution of 2 millimeters. The maximum grade strength available is 2 Gauss per centimeter, and the readout sampling period is 5 microseconds. What should be the amplitude of the readout gradient? Okay, so you can use gamma over 2 pi is that. So we're just going to go through one example just so you have a sense of how to do this. So GXR, we're solving for that, right? So go ahead and take some time to look at this, and we'll regroup in a few minutes. Okay, let's take a look at this. So, first of all, we're given that the delta t is equal to 5 microseconds, right? And we're asked GXR, right? So what variable do we think we would be solving for? Are we trying to look at, is this related to delta kx? Or is it related to WKX? Which one would be easier to solve for? The W? Okay, that's one option. What about the delta kx, right? Delta kx equals gamma over 2 pi times GXR times delta t, right? So that could also be a lot easier to solve for as well. Um, so in this case, what is delta kx equal to? Anybody? So delta kx equals what? Oops. So are you given enough information to figure out delta kx? Yeah, 1 over the FOV. So that's 1 over 20, right? Okay, so we can just say GXR is equal to 1 over 20 divided by 1 over 4,000 divided by 5 times 10 to the minus 6. Is that right? Okay. So that equals, let's see, we can do this. We have 8 times 10 to the 4. Is that right? One over 40 times 10 to the minus 2 equals 100 over 40 equals 2.5 Gauss per centimeter. So what should the amplitude of the readout gradient be? 2 is the closest answer, right? But here's an actual thing that actually happens in real life that sometimes you actually can't do it, right? Because remember, the maximum gradient is 2 Gauss per centimeters. So in this case, the scanner is going to say, I can't do this. You need to change your request. Okay. So let's say you did this and it did that calculation. What do I need to do now to how should I change my FOV such that the scanner won't complain? Do I need to make my FOV bigger or smaller so the scanner doesn't complain? I need to make this so this is the FOV comes in here, right? So if I make this bigger, it's going to ask for a smaller gradient, right? So typically, if you ask for too small of a gradient, that means the FOV is really small. So delta KX gets big, so it needs a bigger, sorry, if you ask for too small of a field of view, like if I want to image something really small, that requires much higher gradients. So then the scanner might just tell you, I can't do that. So in that case, you have to say, okay, well, then I'm okay with having a bigger field of view. Okay. So that's why, like on a human imaging system where things are about this big, the gradients tend to be much less than if you go to like something where you want to scan mice, right? So on our scanner that we use to scan mice, the gradient strength is much, much stronger, right? Because the field of view is much smaller. And so you need the delta KXs and the delta K values are much higher. And so you need much stronger gradients to get that. All right. So that's one of the trade-offs. Yep. Question. Well, so that's a good question. What's the other parameter we could have changed instead of field of view? If I want to have a field of view of 20, let's say I really want a field of view of 20 centimeters, right? So what's the other parameter I can change here? Delta T. Yeah. So the other option is I could make delta T longer. Okay. So that's the other option you could do. But then if I increase delta T, that means scan time is going to increase, right? And for certain objects, if I have to make delta T 100 times as long, for example, my MR signal might die away before I can collect it. So these are the trade-offs we're always against. We're always trying to remember, and we'll revisit relaxation in a few lectures, but things are always dying away. So it's not like we can sit around for like an hour and just collect our data. Every time we create the MR signal, it's going to last for anywhere from microseconds to milliseconds, and then it's gone. So we've got to collect that data. So that delta T can't be like 1 second, right? Because then you basically have no data. Okay. Okay. Let's skip that. So let's just touch upon a little bit of phasing code, and then I'll switch into talking about project two and answer questions about project two. Okay, so remember the phasing code is the thing that's making us the delta KYs, right? It's going from this line to this line to this line to this line to this line, right? So it's related to my delta KY and my WKY, all right? So let's look at first at the delta KX, the delta KY. So that's the phasing cogradient. It's going to depend on two things. It's going to depend on the width of my phasing cogradient, the temporal width, like how long do I play that phasing cogradient out? And it also depends on how much do I change the amplitude every time I play out the phasing cogradient. Because remember that amplitude is changing with time. So that's telling me you need to change the amplitude by this amount each time to get that delta KY. So that this incremental area here is this area here, okay? So every time I increase the amplitude by a certain amount, that's the incremental area that I get. So I've got my GYI, tau I, and I just multiply by gamma over 2 pi. So in this case, if I'm given the field of view, I figure out my delta KY, and I plug into there, and I can solve for either GYI or tau I. So once again, typically you're going to solve for one of these things, right? So let's look at example here. In this case, I'm just given tau sub y is 4 milliseconds. That's a reasonable amount of time. Okay, it's on the millisecond range, so I know my MR signals. There's still going to be MR signal there, and so here, basically, I take this field of view. I'm given that, and I'm given tau sub y. So I'm just going to be solving for this guy, GYI. And so if I plug in all the numbers, I get GYI equals something pretty small, 0.00224 Gauss per centimeter. Right. So once again, just applied the design equation and looking at that. Now let's look at resolution. The resolution depends on how many lines I acquire, right? So basically, how far do I go out along the KY dimension? And so we know that if I'm given resolution, that's 1 over the width in K space, and that's equal to 2 times KY max, right? And so that would be given by sort of the maximum gradient I play out. Let's call that GYP. The biggest phasing curve gradient I play out, that's the one that's going to take me farthest out in K space, right? So when I know the tau sub y and the GYP, I know how far up K space I'm going to go. It's just going to be determined by that area there, okay? And then because it's uh, this factor of 2 comes about because the width is determined how far I go up this way and how far I go up that way. So if I assume they're equal, then I just multiply by 2. And so for your homeworks, that's a reasonable assumption to make. Okay, so let's look at this example here. So remember, I know my resolution typically. I was given tau sub y before, and I'm just going to solve for gy of p here. Okay, and if I solve for it, I get 0.2868 Gauss per centimeters. Okay, and it turns out that that's just equal to the number of phasing codes NP divided by 2 times my incremental gradient, which sort of makes sense. If I know I need to have 256 samples, I need to go out this far, 120 this far, and 120 that far in terms of samples. Yep, question. These colorful boxes, remember, are each time I play out the gradient. Those are the colorful boxes from like 15 slides ago. Okay, so one box might be here, and then the next time I play it out, maybe it's like this. Okay, so like it's the size of the gradient I play out. So here, one time I might play out this gradient, and the other time I play out this gradient. Yeah, yeah. So just showing that there's different steps of gradients I have to play out. So that phasing curve gradient is changing from scan to scan. All right. Yeah, the GYI is the increment of the gradient. Yeah. Okay. So yeah, I think let's see. Let's end here for now. And are there any questions about what we've gone over before we start talking about project 2? Okay. So let me switch gears here. Bring up project 2. Whoops. Okay, everyone see that okay? Okay. Okay, so the timing of it is the um instead of having the live question sessions during the class, we're going to have it during the whoops. We're going to have it during the final period. So here we're going to have the live question. Whoops. Let me get this to work. Okay, so live question period was basically during the final exam period. So it'll be in this room, and we're going to do it in person. So you would and we'll send out logistics as we get closer, but essentially you would just need to make sure that you're in the room long enough such that we have to switch up the order a little bit. You're within proximity of the time. Okay. So as with before, all groups have to submit a recorded presentation, but only half the groups will have live question period. All right. So any questions about the schedule? Okay.
For the report, do they need to create do they have time for a timer?
Do they have to be present?
Yeah.
No, you don't have to be present. Yeah. Um, okay. I think it's basically the same groups as before, but if you need to switch groups, let us know. The main timing is that basically by next Monday before class, submit your project proposals on Gradescope. And in this, because it's a little, the MR project's going to be a little more diverse and sort of all over the place, like you will get feedback on your project proposals. And generally feedback is you're trying to do too much or I have no idea what you're doing. So the idea is to give you feedback so you're not surprised by the evaluation at the end. Okay. So I will try to give you feedback and then generally ask you to send updated proposals via email so that we can go back and forth and have a conversation via email. Now, if you don't get if I say project looks good, then you're done. Okay. But if you get feedback, uh, you're not required to respond to the feedback. But if you don't, then it generally you would have to realize that the project is probably out of scope or you know, it would benefit from following the feedback. So the feedback is there to help you come up with a project that would tend to score fairly well. All right. So that's due. So your initial project proposal is due next Monday, but uh, and some groups have already contacted me. Feel free to contact me beforehand if you want to talk about an idea for a project, or you can even send me a draft by email and say, hey, could you take a look at this before we submit? Okay. Because I think it's much better to get feedback beforehand than to get surprised at the end. All right. So any questions about that? Okay. And then there's just a lot of sort of little things that I would certainly recommend reading through this. Part of a lot of these things are sort of have similar with past years, what we've done, but we have changed things up a little bit. So I'll talk a little bit about sort of these things, which is in general, I mean, point B is it's sort of good to ask yourself, does your presentation require course principles to understand? And the grading criteria will include a clear connection to course content, quality of engineering content and level of difficulty, and also clear documentation and organization of all submitted slides and code. All right. And you can read through, I think this was posted last night. You can read through the rest at your own leisure. A lot of this is just meant to sort of help give guidance, similar to what Professor McVeigh did about, when you make up your slides, just make sure to check that, the recordings show the slides, that you're not obscuring things, that you're numbering things. Also for the code, we spent a lot of time looking through code and trying to figure out what was going on. So just the better you document your code, the more we can give you credit for what you did. If we can't find what you did, or we have no idea what code went with one figure, it's hard to sort of give you credit for that. Okay. And also for data, if it's a reasonable size, please upload that. Um, this just had sort of a historical link to some strong projects. So if you're looking for some projects that would certainly do well, then the compressed sensing and pills talks from 2021 are certainly good examples to look at. Okay. So there are sort of a huge range of topics you could do. So if you want to do something that is sort of free ranging, feel free to pick from this list of topics or any other area you're interested in. But if you're looking for something of a more of a guided thing, then option two is what certain groups have done, which is in many years ago, we used to have all the groups do all the same projects. And these are more guided experiences where it's sort of, you just follow along and you sort of, they're not easy to do by any means, but at least you know that, if you do them, you're sort of satisfying the difficulty criterion. All right. And those would tend to be, I think as said in the announcements, uh, we don't want too many, I mean, we would like some diversity of projects. So if too many groups want to do the same projects, we will give feedback like, hey, we already have two groups doing this project. You could pick something slightly different. There's lots of resources online, so please feel to use those. And obviously, ChatGPT and other AI is totally usable. But I do believe I think there's a statement in your references. If you use AI to generate your code or slides, just make a concise summary on the last slide about how you used it, and therefore. You don't have to discuss it in depth while you're in your recording, but just present a slide saying, we use this and this. The caveat is AI is great, but as I sort of saw by looking through some of the code, it the probability of it giving you the right answer is not super high as of today. Okay. So just be aware. It's really good for learning principles and showing you examples of what to do and giving you guidance. But if you count on it to get the code correct, you might get lucky, but you might also spend time, hours and hours debugging code that's just wrong. And so just be aware of that. And so I would suggest, just sort of doing things that are not super broad or super complicated. Just pick a small area that you'd like to do and do it well. And that tends to be the best use of your time. You'll actually learn something and your project will tend to score fairly well. All right. So any general questions before we conclude for today about the project? Okay. So if you have any questions, I'll stick around here for office hours. Otherwise, we'll see you on Wednesday. All right. Thanks.